The calculations for simple linear regression. The calculations for simple linear regression help determine if there is evidence of a relationship between two quantitative variables in the population and to evaluate how strong that relationship is. They also allow us to estimate the effect of x, the independent variable, on y, the dependent variable, and to predict values of y based on values of x. The first step is to calculate the regression coefficients b0 and b1, which are the intercept and slope of the line that minimizes the total sum of squared error from the points to the line. If performing calculations by hand, formulas for B0 and B1 can be used. However, these calculations are almost always done with Excel or statistical software, usually found under regression, linear regression, or simple regression. And it is relatively straightforward to obtain the regression coefficients as long as the correct variables are specified as the independent x and the dependent y. For example, if we have a small sample of 6 data points, x equals 1, y equals 4, then x equals 2, y equals 3, and then 4 and 8, 6 and 10, 7 and 9, and 10 and 8, then using Excel's data analysis tool, selecting regression, and specifying the appropriate x and y variables, the regression output is generated and we find the intercept B0 equals 3.875 and the slope B1 is 0.625. Once we have the coefficients of the regression line, B0 and B1, based on the sample, we should test if there is evidence of a significant relationship between x and y in the population. This test is necessary because it is possible for there to be no discernible relationship in the population, which would occur if beta 1, the true population slope, equals 0, but it happened by chance that our sample appeared to suggest a non-zero slope. Therefore, we test the null that beta 1 equals 0, meaning no relationship exists, against the alternative that beta 1 does not equal 0, which means a relationship does exist. The test statistic is a t with n minus 2 degrees of freedom, where n is the sample size, and t equals b1 minus beta 1 divided by sb1, or b1 minus 0 divided by sb1, where sb1 is the standard error of the slope, which is essentially a standard deviation of the estimate. Thus, the test statistic basically tells us how many standard deviations the sample slope b1 is from 0. The value for SB1 is always part of the regression output from any statistical software or from Excel and is often found next to the estimate of B1 under a column labeled standard error or STD period error. In our example from Excel, we see the standard error of B1 has value 0.2845. Thus, we can calculate the test statistic T equals B1 minus 0 over SB1, which equals 0.625 divided by 0.2845, which equals 2.197. This value, incidentally, is also shown on the regression output, usually under T or T-stat, depending on the software. For example, in Excel, we see a column to the right of the standard error called T-stat. To determine if there is evidence to reject the null that the true population slope equals 0, a p-value approach is usually used. Here the p-value is the area to the outside of the values of the test statistic and its negative on a t with n minus 2 degrees of freedom. In our example, the sample size is 6, so we have 4 degrees of freedom with a test statistic of 2.197. Thus, the p-value is about 0.093. Again, conveniently, the output from statistical software or Excel shows the p-value associated with the test statistic next to the value of the t-stat and often in a column labeled as p-value or sig, standing for significance. As with any other hypothesis test, we reject the null when the p-value is less than the significance level alpha. For example, if we used alpha equals 0.10, since the p-value is 0.093, we would reject the null that says beta 1 equals 0, and we conclude there is evidence of a relationship between x and y in the population. Next, we may wish to evaluate how strong the relationship is between x and y. We can use the correlation coefficient and/or the value of r squared, which tells a percentage of variation in y that is explained by x. Values of r squared closer to 100% or 1 are better, since they indicate that x does a better job of explaining variation in y. The correlation coefficient can be calculated based on the sample x and y values, but is also shown in the regression output. For example, in Excel, we see r labeled as multiple r under regression statistics. In our example, a correlation of 0.7395 indicates a fairly strong positive relationship between x and y. R squared can be calculated by squaring the value of r, or by calculating the ratio of the sum of squares regression SSR divided by the sum of squares total SST, which are both shown in the ANOVA table of the regression output. However, the value of r squared is shown in any regression output and is usually read directly. For example, in Excel, we see r squared shown in the summary statistics. For this sample data, r squared equals 0.5469. Generally, we would say that r squared over 70% or 80% would indicate a strong or accurate regression model, and over 50% would indicate a mediocre one. Often, an R-squared value under 50% would lead one to conclude the model is not very good or accurate. However, the interpretation ultimately depends on the application. For this example, an R-squared of 54.69% would indicate a mediocre but not a great regression model. Another calculation often done in simple regression is the interpretation of the value of B1, the sample slope. B1 represents the estimated increase in y as the x value increases by 1 unit. That is, change in y divided by change in x, sometimes referred to as rise over run. In our example, B1 equals 0.625, so we would estimate that the value of y increases by about 0.625 when x increases by 1 unit. Sometimes we might want to know what the estimated change in y is if x increases by some number of units other than 1. In this case, we take that number of units and multiply by the value of b1. For example, to estimate how much y will change if x increases by 10 units, we take 0.625 times 10, which is about 6.25. The final type of calculation that is often done in simple regression is to predict the value of the dependent variable y based on a given value of the independent variable x. In this situation, we simply use the regression equation y hat equals b0 plus b1x and substitute the estimated regression coefficients in the value of x as appropriate. For example, we might wish to predict what the value of y would be if x were equal to 5, so we would have y hat equals 3.875 plus 0.625 times 5, and we estimate that y would be about 7 when x equals 5.